bisectors, right? We've been introduced to bisectors. What I want to start with is the definition of a perpendicular bisector. Okay, so this is the definition. So this is something that would go on like your review sheet or your flashcards as the definition of a perpendicular bisector. It's a line, a segment, a ray, or a plane that passes through the midpoint of a side of a triangle and is perpendicular to that side. Okay, so here we have a triangle ABC, and what we're going to do is we're going to try to draw a perpendicular bisector right there. Okay, so measure how long BC is, right? And if you measure it, how many centimeters is it when you measure on your piece of paper? It's about 5 centimeters, right? So, okay, so divide that by 2. So if it's 5, half of it is 2.5. If it's 5.5, half of it is 2.75, 2 3/4. So you would go, right, to 2 3/4, and you would put a dot there. That is the midpoint. Okay, so that is the midpoint. These are centimeters. We'll say each is 1 millimeter. Each dot is 1 millimeter, but this is a centimeter.
Where do you want me to put a dot
at? This is the midpoint. This part and this part are congruent to each other. And here we want to make a 90-degree angle, right? A 90-degree angle like this. And so if you use your ruler and you extend that line, okay, that is a perpendicular bisector, because it is a line or a segment or a ray that divides BC into 2. It's a bisector, segment bisector, but it's also perpendicular to it, so it's a perpendicular bisector. Okay? Now, the perpendicular bisector theorem says this: if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So this line here, CD, do you see how it's perpendicular to AB, and it's the perpendicular bisector. Okay. Now, if you close your eyes and you pick any point on that red line, okay, we're going to use this C here. Draw a line from A to C. Use your ruler to draw a line from A to C and measure that line. Then draw a line from C to B using your ruler and measure that line and tell me what you get. The theorem says that the distance from any point on the perpendicular bisector is the same to either of the endpoints. Okay? Now, if you choose any other point, if you were to choose a point on the bottom, like D, and if you draw a line to one endpoint of the segment and to the other endpoint of the segment, those two are also going to be congruent. All right? And like I was saying before, if I close my eyes, pick a random point, all right, that's going to be the same distance from one endpoint and then to the other endpoint. Okay, so if CD is the perpendicular bisector of AB, that means AC is congruent to CB and AD is congruent to DB. Okay? All right. Now, let's prove that theorem. Let's prove the perpendicular bisector theorem. What we're told here is CD is the perpendicular bisector of AB. All right? CD is the perpendicular bisector of AB. We're going to prove that AC is the same as BC. Okay? All right. Well, when I draw AC and BC, what do I get? Two triangles, right? So I can totally do this. All right. So now, number one, CD is the perpendicular bisector of AB, and I get given. Now, so what does that mean? That means this and this are congruent to each other, right? So number two, so perpendicular bisector means those are congruent to each other, and also that these are right angles over here, right? So number two, look, I can say I'm going to add a point here, E. Okay? AE is congruent to EB, and angle AEC and angle BEC are right angles. Okay? These two together are the definition of perpendicular bisector. So this is not segment bisector. This is perpendicular bisector. So it's got two things that come with it. All right? Yeah.
If we're proving the perpendicular bisector theorem,
This is the definition, not the theorem.
oh.
Yeah? Good question though, but that's the definition. Okay, so now that we've established these are right angles, I can say angle AEC is congruent to angle BEC. All right? Because all right angles are congruent. So now, I've got a side here that's congruent. I've got an angle here that's congruent. What else do I have? A side here, CE, is congruent to CE. Why? Reflexive. And finally, triangle ACE is congruent to triangle BCE. Why? SAS. And then AC is congruent to BC, CPCTC. Right? So that's how we prove the perpendicular bisector theorem. Because look, if C was higher or lower, would anything have changed? No. Okay? All right. So let's apply it. Solve for X if SR is a perpendicular bisector. Okay? Well, if it's a perpendicular bisector, then the distances from each endpoint to the R are the same, right? So these two are congruent. So I can say 2x plus 3 is 4x minus 7. 2x is 10. X is 5. And so here it says to solve for x and RT. And what's RT? Right, 4 times 5 minus 7, 13. All right. Okay, now, of course, every theorem has a converse, right? So let's talk about the converse of the perpendicular bisector theorem. All right, let's read this. If a point C, here we go, okay, is equidistant, same distance, from the end point of a segment, okay? So if C is the same distance from the end points of a segment, Okay, so if those two are congruent, then it is on the perpendicular bisector of the segment. All right? So if you have a setup like this and AC and CB are congruent, then I know, right, that CD is the perpendicular bisector of AB. All right? All right. So let's talk about, okay, when is that useful, right? Let's talk about when that's useful. So suppose you have, what type of triangle is this? Isosceles triangle. Suppose I draw a line through here. Now this vertex is on that line, correct? On that red line. And that point is the same distance from this endpoint as it is from that endpoint, correct? So what does that mean about the red line? It's a perpendicular bisector. It means this is perpendicular and these two are congruent. Okay? All right, let's talk about angle bisectors. An angle bisector is a ray planar segment that divides the vertex of a triangle into two congruent angles. So we're going to draw the angle bisector for B. I want you to draw a line here through B that just divides B into two congruent parts like this, right? And when you continue that, it passes through this point, okay? The purpose of the angle bisector is only to divide that angle into two. There are no guarantees that it's going to be perpendicular to this. There are no guarantees that it's going to be a midpoint to AC, okay? All right? So here, no guarantee. Yeah, but yeah, my line, right, because I only, when I'm gonna cut it in half, I only visualize, like, I only look at that part of the angle. My goal is just to cut that angle in half, and then it lands where it lands. That's what I'm saying. There's no guarantee that this is the midpoint or perpendicular, okay? All right, so here, given that AD is an angle bisector, the minute I see angle bisector, reflexively, I do this, all right? Find the measure of angle ADC, this one, okay? All right, so let's focus on the big triangle. If this is 66 and this is 50, together, that's 116. 180 minus 116 is how much? 64. So this whole thing is 64. And you divide that by 2, so this is 32. This is 32. And now let's focus on this triangle. Right? Measure of angle ADC. Okay, well, there's actually a couple of different ways we can do it. One is you can focus on that triangle and you can say it's 180 minus 50 minus 32. That'll give you 98. Yeah.
Can't you also do 66 plus 32?
Precisely. You can also say, hey, this is an exterior angle, and you could say that it's equal to those two. Okay, good. All right, next one. Angle bisector theorem. Okay. Yeah. If a point is on the angle bisector of an angle, then it is equidistant from the sides. So look, this is the angle bisector, okay? Cuts the angle in half. I pick a point at random. That point is the same distance from here as it is from there, okay? Those two are congruent, all right? So if you cut an angle in half, pick any point, it's going to be the same distance to one side of the angle as it is to the other side of the angle. AB, that means what and what are equal? BC is congruent to CD. Okay? All right, so let's prove it. All right, prove the angle bisector theorem. All right? So look at what we have here. Let's write down this given. CD is an angle bisector. And then EG is perpendicular to BC. EF perpendicular to AC. Okay, and we're going to take a moment and mark all of this stuff on our diagram. All right, so we start with what we're given, right? I'm given CD is an angle bisector. That means those two angles here are congruent to each other. So angle GCE is congruent to angle ECF. Definition of angle bisector. Okay. Now, I'm told that these two angles, these two sides are perpendicular, so I gotta give my right angles now, right? So number 3. Angle EGC and angle EFC are right angles. So this is the definition of perpendicular lines. All right, I need to prove this and this are congruent. And so you see how I have like 2 mini triangles here, right? Same thing, I want to see if those triangles can be congruent to each other. Well, so far I have an angle, right? Yeah. EC is congruent to EC, precisely. And also, if these two are right angles, then they're congruent to each other, aren't they? So, next one here, I'm going to say angle EGC is congruent to angle EFC. All right angles congruent. EC congruent to EC, reflexive. So finally, those two triangles are congruent. Triangle EGC congruent to triangle EFC. What is the reason? Other way. AAS. EF, so finally EF can be congruent to EG, CPCTC. Huh? Yeah. If BD is an angle bisector, right? We need X and EF. Okay, so ED is an angle bisector. These two are congruent. And any point on the angle bisector is the same distance to one side as it is to the other side. So those two little segments are congruent to each other. So 2x plus 6 is equal to 4x minus 1. 7 equals 2x. X is 7 over 2. So EF is 4 times 7 over 2 minus 1. And that is 13. Okay. All right. Converse. Yay. Okay. If a point is in the interior of an angle, and if that point is equidistant from the sides of the angle, so C is inside the angle, and it's the same distance from the sides of the angle, then we say that C lies on the angle bisector. So if we get a point C and it's the same distance, if CB is the same distance as CD, then I say AC, ray AC is an angle bisector. Okay? All right. So, is there enough information in each of these diagrams to find the value of x? So look at this one. Is there enough information there? Yeah, why? Right. Fabulous. What about the other one? What's missing? This is a, huh? What does it look like?
The angles have to be.
Not the angles.
The sides.
Which sides?
Like the axis of the rest. Left.
Okay. So this is definitely a perpendicular line, right? What's missing is that these two should be congruent to each other. Then it'll be a perpendicular bisector, because right now it's just a perpendicular line. If it was a perpendicular bisector, then we could say these two are congruent. Okay? So no, it's missing these, okay, in order for it to be called a perpendicular bisector. All right? Okay, so we'll stop there.